Good good evening. Good evening, everyone. Um, quick note. Yes, I am doing well. Thank you. Sorry about the glitch for the test again. But I gave you guys a couple extra days to get it done. So sorry again. Um, so far, a lot of people are doing well on it. Um, so right now, you're looking at a high A, looking at a low A average. So it's not like I said, it's not a difficult test. But I need to check the calendar because I can't remember if spring break is next week. Since y'all already had, winter break this semester, I'm thinking that spring break is going to be canceled. So, because we're already behind. Yeah, so it's not next week; it's the week after. All right, cool. But we're gonna go and just cancel spring break this semester. There you go. Yeah, we're gonna cancel spring break. So don't worry about having spring break. No, I'm just playing, y'all. I'm just joking. I'm just kidding. I wish I could cancel it though, because we're so far behind. But we're gonna catch up. We're gonna catch up. Y'all getting 2 labs. Y'all gonna have 2 labs. Yeah, I know. I know, Cassandra. I'm sad too. I'm sad too. But y'all gonna get 2 labs. Go ahead, Lawson.
For the Bridge Lab notebook, is
Hmm.
that is it? It says it's due tomorrow night. I don't know if that's like if it's changed to go along with the actual like Bridge Lab submission of next Friday.
Yeah. I'll change it. It's due next Friday.
Oh,
Or
okay. Yeah.
I think that whenever I assign to do that, it'll be a due with the actual lab.
Okay, yeah, because right now it says it was due tomorrow and the other one was due next Friday, and so I was trying to finish it up.
Oh, okay. Yeah, man. Nah, don't worry about it.
All
Yeah.
right, appreciate it.
Okay. Yeah, I'll fix that. Thanks, Lawson. And thanks everyone that emailed me about the exam. It wasn't the majority of the class. It was just a few you. It's just a few. Uh, it's due tomorrow night. So you got an extra day to get it done. Again, spring break is not next week, so it's the week after. Thanks. Uh, I think your name is, how you say your name? Sahil? I think Sahil. He starts from 20. All right, Sahil. Yeah, thanks. Um, Let me correct that lab notebook real quick. Since we're on labs, I guess I'll just start with the labs. Um, so again, it's due in 2 hours. Ah, so I got my dates mixed up because I thought I changed it to tomorrow. Let me change that real quick too. No, no worries. I can change it on demand. um, Man, the calendar is just so weird. Like I'll be trying to do too many things at one time, honestly. So I end up messing up stuff. That's what happened when I did when I made the exam. All right, now it's due tomorrow night. But yeah, so due tomorrow night. And since we're on labs, let's just go ahead and jump into labs. The lecture isn't gonna be too long. It's a really quick lecture. So we have the boat lab, but let me start with the bridge lab. So the bridge lab, if you all can see my screen. I started talking about this, I believe, last week. And the gist of this is to design. So let me start up. You're gonna pick, I guess, either toothpick straws. Even you can even use paper. That semester, I had some of my students use paper. So to design a truss frame bridge, right? And you're gonna span this bridge. Like I said, you can either use books, you can use a table, depending on how long you make it. Which let's go into the design criteria, which is right here. It says so you can design, build, and test a bridge that can span, go over a length without touching anything. And I'm gonna explain what that means. Without touching anything, a length that is 8 times the length of your longest building material. All right, so the building material again could be a toothpick, a straw, or a sheet of paper if you don't have straws or toothpicks. All right. Now the length of that leg, right? So however many legs you have. So say you have, I don't know, 100 legs or so, and your length, it could be 8 times the length of your longest building material. So if you make I think I even have a limit on the building material. Let's see, what did I make your building material? So if you use a toothpick, which is 5 centimeters, right? And then so your longest length, meaning your entire bridge, would have to span 40 centimeters. But if you say you cut a sheet of paper and you say, I don't really know the metric system very well, so I'm gonna measure it in imperial, and you cut a 5-inch sheet of paper and you made your longest member 5 inches. And so the bridge would span 40 inches, if that makes sense. So this is the spanning. It's going to span across either 2 books, 2 chairs, 2 tables, whatever you choose. And you're going to make it so if you have, like, say that's one of your members, that line right there, and you say, I'm going to make my longest member 8 inches. And so then you could span across 64 inches. Now that's pretty long. So I don't suggest you all doing that. 40 centimeters. So in class, it would be roughly 40 inches in class between the 2 tables. So 40 inches would probably be your max that I would say do, but you don't have to do it that long. You can go 5 to 10 inches, to be honest with you, because 40 centimeters is not that long, for the entire bridge, that is. So with that being said, you're going to use some type of a weight to weigh it down. And in your case, hey, you can use coins, and you just got to just figure out how much the coins weigh. And you can, let me backtrack. Sorry. So when it says not touching, it doesn't, because that doesn't make sense. It means you have to touch. But what we're saying is you can't anchor it on either side. So like you can't use you can't tape it down, right? You can't use a weight to hold down your paper on either side of the books. You can't. It just has to basically be free. So in other words, you got to create a design to where your bridge is going to actually stay on both sides, or hold up on either side of the books or table or chairs or whatever you use to mount your bridge to. So it's like you're not really anchoring it down. You're just sort of laying it on over 2 different things. Does anybody have a question on that? Does that make sense? It doesn't. It doesn't make sense. All right, good. All right, good. Okay. Um, Now, also, in addition to that, you're going to calculate the cost, right? Calculate the cost of your bridge with each member costing $1,000. So for each leg, you use for your bridge is going to cost $1,000. Okay. And each node costs 3,000. So what does that mean? Each node is the sections that you're using to create one leg or one arm of a truss. So say you used a node, like say you use glue. So if you glued one piece of a truss, let me go to my handy dandy whiteboard because I like my whiteboard. And I know most of you are probably visual learners. So you have, and don't mind the jaggedness. It's all gonna make sense in a little bit, maybe. So these little circles that I'm drawing are nodes or joints, right? So they connect your member. What are you gonna use to connect your member? Are you gonna use glue or tape? I think I said use tape, but hey, it's been a crazy year starting out. I'm gonna say you can use glue, okay? So you can glue one leg of your truss together. All right. And however you decide to build your truss bridge, it's up to you. So then if I were to go across, that's fine. It's okay. You can use glue. We're going to go with glue. And, don't mind. This is like a paper bridge. That's why, you know what I mean? It's so wavy looking because, paper is hard to make paper straight. And then it's not sturdy. So all of these little wiggly lines because I just drew you a paper bridge. Okay. All right. With that being said, you're going to have your spans, all right, or what have you. It's actually should be touching. It's not like what I said in the little thing. It's not touching. No, it is. It's touching. Okay, but it's not anchored, right? You don't have a weight. There's no weight here. Okay, it's just spanning across. Now, you can put your weights though in the middle or along here, along the joints. You can put your weights there. And you got to determine how much your bridge can hold up. If your bridge doesn't hold up anything, then hey, you got to make note of that in your lab report. And then you got to explain to me what you could have done better to possibly make your bridge hold up or hold some type of weight, hold 1 penny at most. And if you say, well, it's because my material, I use paper, I didn't have anything else. And say, well, explain that. Just my building materials were just too flimsy. Also, when we talk about cost, so each one of these nodes or these sections that you glue together would be worth 3,000 each. So with that being said, you're going to have to calculate the total cost of building your bridge and then give sort of like a synopsis on how you spent so much money and your bridge was able to hold up so much weight, right? And explain how, basically correlate the cost versus the outcome or how efficient your bridge was. Like I spent a bunch of money, but my bridge was very sturdy or very efficient when it came to being, a bridge. I couldn't actually, walk across that thing, but I did spend a lot of money though. So that's going to result in a lower grade, right? Trust me, it's not like it's not. It's not. I should count against you, but I'm not. But what I want you to see is just from an engineering standpoint, how to optimize, right? And so when you're looking at optimize, you're maximizing something, but you're minimizing something. Okay, and so you're getting the most out of your material, but I'm not using a lot of material, right? So that will be optimization. But yeah, so that's what I want you to really think about and consider as you're doing this particular bridge or you're doing this particular lab experiment. All right, any questions? No, There is no cost limit. So if you spend $1 million and your bridge doesn't hold 1 penny, yeah, you're not gonna get a good grade. Just saying. Just saying, Cassandra. So be wise in your building and spending. Yes, be wise in your building and spending. All right. So let's look at this other lab. Let's see. Everybody good on the bridge lab? No other questions? All right, cool. Oh, he said he's gonna dump it in the bear. Oh, let me share this. I know you all have probably looked at it, but I just wanted to bring it up. So the lab notebook is where you do all of your designing. So you say you can compute your cost. You can and we're on the bridge lab. So you can talk about how much material you're going to use, how it's going to span, uh, the length of each member. You can discuss your if you're going to add glue, you're going to use tape, you're going to use a combination of both. They both cost $3,000. And then there's this simulator. So the simulator is meant to help you um, design your bridge, but it's really just a fun little tool where you can build a bridge. So I would just be like, whatever. I mean, I shouldn't say that. I'm recording this, but you can't. We're saying use the simulator, and you can get some calculations from it, and then just add it to your appendix. But the simulator really isn't going to, because it depends on the material. You can't pick your material in the simulator. All you're doing is putting together some lines and then putting a weight on it, and then it runs some numbers to show you, how much of a load or how much resistance or how much stress is being placed on your bridge or what have you. Okay, so you can calculate those by hand, or really, it's not really worth it. Just tell me how much weight your bridge held. So everybody get on that sample notebook. All right, take your silences. Yes. Okay, boat lab. Now, this is a fun lab. All right, I like the boat lab because it's quick, it's easy, it's simple. Um, real simple, and it's not a lot of thought that goes into it. A little bit of thought, but not a lot of thought. So in the boat lab, what you're going to do is you're going to get some aluminum sheets. Okay. Um, and then you're going to cut 5 by 5 inch squares of aluminum foil. Okay, so you're going to need something, a plastic tub. You can do it in your sink. A lot of students did it in their sink last semester. You could do it in your tub again. But if you got like the little plastic little bins that you can put water in, you can use those as well. So what you're going to be doing with these aluminum foil 5 by 5 inch sheets, square sheets, is designing some type of a boat with it. Now you can get as creative as you possibly can with this particular assignment or experiment. You can design your boat like the Titanic. You can just, hey, make it into a square sheet or whatever. You can do it however you want to do it, but you can only use one sheet per boat. All right. But it's 5. You got a total of 5 different boats that you can design. So I would suggest, as a team, if you got 4 people on your team, your lab group, each of you do one, and then one person will do 2. All right. If it's 3 of you, then 2 of you, 2 of you do 2, then 1 of you do 1, or what have you. You can just divvy up the work, just be like, hey, I designed 2 boats. But I'm just playing. It doesn't matter how you all divvy up the work, but you could just divvy up how you design them. And when I say design them, it's more or less how you're going to shape them. Okay, the shapes you're going to make each of the aluminum foils into. Now, kicker, you're going to have to use pennies to place inside of these little boats, though, because that's what's going to determine how much weight your boat will actually hold. So this is kind of cool. You're doing 2 kind of weighted experiments. One is a bridge, another is a boat. And what we're really looking at here is buoyancy, right? So I know we haven't really discussed a lot about buoyancy, But that's what you're reviewing here. You're reviewing buoyancy force. So what you're going to do is you're going to find out the weight of a penny. If you have dimes, weight of a dime. If you got quarters, hey, your boat ain't going to last very long. But you could look up the weight of quarters. No dollars, because you don't want to get your dollars wet. Okay, so that would be wise. But even if you have little weighted objects, something that you know the weight of, and you have multiple of them, you can use those also. And so the gist of it is you get your little boat ready, get your little water ready, put your boat in the water, and then you start filling it with some type of a weight. And then and then count the weights until it sinks. So if it sinks at 10 pennies, then it held 9 pennies. All right. So on and so forth. Any questions?
No, sir.
Oh yeah, you good.
Do we need to record the process for for the bridge and for the boat? Like what is happening, or just write it down in the notebook?
Yeah, just write it down in a notebook. I mean, if y'all want to do a video and share with me, I mean, I'll look at it. I'll laugh. I get a kick out of it. I do miss the in-person experiments. They were so fun. So, but if y'all just want to share it, I'll send y'all some, that was horrible. That was some junk. No, I'm just kidding. I wouldn't, I wouldn't do that. I wouldn't do But yeah, it's up to you guys if y'all want to do a video. All right. Any other questions? All righty. So then let's jump. Oh, go ahead. Oh, wow. So I will forward you their email address. How about that? That's not good. Yeah, I'll forward you their email addresses. So, oh, so y'all two are in a group? Jacob and Sahil? Oh, good. Well, there you go. Jacob, share your information. I can't remember who else who else I put with you guys. Um, I'll have to look it up. But yeah, and then also if y'all wanted to do your lab during the time here, I can set you guys up in groups so y'all can talk. Okay. Yeah, Andrew, he hasn't been in for a while. He's been doing some of the he has done some assignments, but I haven't seen him actually come on to our scheduled classes. So I'll have to send you his email address. But again, I can set you guys up in groups after our lecture if you want. And I'll just break you guys up. You all can talk. You all can share videos. I can come in and be like, hey, you need any help? Or so on and so forth. So I can do that too. I just have to figure out who's all in the lab together. And so y'all that'd be cool too. Just do our breakout sessions so y'all can see how we do that. Yeah, I'll do that. No worries. Yeah. Nah, I'm not doing it right now. I'm about to run through this lecture. All right, so let's jump into this lecture. Like I said, it's a fun lecture. I like this lecture. It's fun for mechanicals anyway. If you're not a mechanical, it's still fun, but you don't have to worry about doing it ever in your career. Um, all All right. Now, chapter 16 is engineering drawings and symbols. Engineering drawings and symbols. You know, we talked about communicating, I believe, in chapter 4, which was about 3 weeks ago now. And I discussed that as engineers, you're going to communicate through CAD, computer-aided design, or right, computer-aided drawings, or computer-aided modeling, or what have you. And this chapter talks about computer-aided design using symbols and drawings, mechanical drawings, electrical drawings, civil engineering drawings, and how we come about doing those from using computer is AutoCAD, SolidWorks, things like that. I'm not sure what chemicals used, but you all use some kind of thing to model flow and things of that nature. Civil, I'm not sure what you guys use either. But architects and civil engineers, I think they use like a similar one. But mechanical engineering and we use, and even electrical engineers use AutoCAD and some type of a 2D modeling software where you can come up with schematics to showcase circuits and things of that nature. But here we're going to talk about doing orthographic views by hand. All right. An orthographic view. What is an orthographic view? Orthographic view just shows the object's projection. Basically, I'll say it in this term. An orthographic view gives you views, because I really like that definition. It gives you views or gives the machinist a view of the object you're wanting to get machined. All right. So in this view or in these orthographic views, it's going to capture every view of the object with the dimensions that are the showcase dimensions of that object so that they can machine it. All right. That's orthographic views. It's going to capture all of the dimensions of an object that a machinist can see and then build the object from those views. So what we have here, you got, now, let me backtrack. When you look at an object, you got a front, you got two sides, you got a top, you got a bottom, and you have a back. Doesn't matter what object you have. Every object has that. That's just 3D. That's 3 dimensions, right? I know I gave you multiple sides, but I gave you a complete full ortho view or 3-dimensional view of yourself, right? You have a front, you have a back, you have a top, you have a bottom, and you got some sides. And so if you're drawing that in a 2-dimensional state on a sheet of paper, that is, this is how it would look, like this. So if you were to draw yourself in 2D, and this was your face, right? That would be your face in 2D. Then you have your top, meaning your top of your head in 2D facing you, right? You'll be looking. This is as if you're looking at the top of your head. And then the bottom of you are your feet, all right? Then you have your sides and then your back. But what we only need, in some cases, 2 of the 3 sides. And then in some other cases, you may need 3 of the sides, right? 3 of the, however many sides this is. This is 6 sides. 3 of the 6 sides in some cases. But in the case of this drawing or this object, you only need 2, right? Because it's showing you everything you need in the top and the front. We got the width, right? That's this. We see the hole. We see how far the hole goes through from the top. We see this dimension of the top head here. We see this thickness from the front, this thickness of this base here. We know the width of that base. It's here, right? And so you really don't need a right view because we know the height too, right? So it gives you the height of this object, the length, the full length or width, gives you the height of this, gives you the whole diameter, shows you how far the hole goes through, gives you the width of the entire thing. So I'm just repeating myself, but that's what a drawing does. So if I were to dimension it, and what all I'm doing when I say dimension is I'm measuring the size of the object. All right. And so you would showcase that in orthographic views. Now, if you've all taken my graphics class, this is pretty simple. You already know all of this stuff. If you haven't taken my graphics class and you've taken somebody else's graphics class, you already know all of this stuff. So you're good to go on that. So when I ask you to draw an orthographic view, this is what I want to see. If I say, hey, of this particular object, I want you to draw an orthographic view in this particular way. And this particular way that you're seeing is third point perspective or third view perspective. Third view perspective mainly just really means you're going to start with a front, you're going to have your top, and you're going to have your right. That's third view perspective or third angle perspective. All right. You have your front, top, and a right. All right. With that being said, I tell my students, because this is a fact, if you're drawing something for a company, this is the way it should look. It's like, what do you mean? Well, it needs to be front. The top is above the front, because if you're looking at the top of the object, it will be on top of the object. Does that make sense? This is the front of the object. On top of the object, if you were looking down on top of it, it will be above the front. And then if you say went to the right, like if you just took your head to the right of the object, that would be the right, and the right would go on the right. Now, a lot of my students will have the top, front, right, and many of you still going to go top, front, right, and that's okay. All right. My students last semester, I didn't take off points, even though I told them in lecture, hey, that's not how you're supposed to do it. They still did it. And then some of you will have top, front, right, all horizontally. And that's okay. It's not okay, but it's okay. Okay. Because I'm just going to say, hey, as long as you know how to draw the views, we're good. You're capturing everything the object has displayed in 3 views. Hey, I'm going to accept it. And I probably shouldn't say that, but I'm saying it. But the correct way to do it is, it should look just like this. Front, a top, but this is third angle perspective. A front, top one above the front, right to the right of the front. All right. Moving right along. Then you have, okay, so let's go over that before I jump. You have various types of lines, okay? So these lines here, they're hidden lines. And the hidden lines is to show you within a different view, right? Things you cannot see. So there may be a case where you have a line in the front of something. It's not one right now, but I'll talk about it later. Okay. So you have this hole here, and you can only see it in this view. So if you go to the right of it, you can't see it, but you know it's a hole there. So what are you going to do? You're going to draw hidden lines. And I want you to notice something too. Everything is lined up, right? If I go to the right, this line stays in the same place. This bottom line stays in the same place. This top line stays in the same place. You see the hole? It stayed in the same place, right? So that's where a ruler comes in. So it gets kind of fun. It goes back to elementary. So you're going to be drawing these lines. You get your little drawing sheet, get your ruler, right? And you're just going to be like drawing stuff. And that's where the graphic paper comes in handy, right? So if you got the graphic paper, it's easy because you got your squares there to help you draw all of these shapes. And it helps you keep everything, it's not really, well, I guess you could say parallel to some degree. Like every line will be parallel, the lines that need to be parallel. And it helps you to keep the lines parallel. All right, any questions? Any questions on orthographic views? Any questions on why we use hidden lines and then solid lines? Solid lines are what we can see. And then you have this line in this circle. That's called a center line. Okay. And then in graphics, they'll show you, we'll have different weights of each of these lines. So each of these lines will have different weights, and the weights is basically different thicknesses, right? So these solid lines are obviously thicker than the hidden lines. And then the center line is probably the same thickness as the solid line. All right. So we talked a little bit about dimensioning and tolerancing. So dimensioning is just the measurements of the object. All right. And so tolerancing, go to this sheet, this visual. Tolerancing is to give your machinist room for, error, right? Because there's always going to be some signs of error within your object. It's just because machine, it's not, nothing's going to ever be perfect. So you want to give a tolerance. And then also with the tolerance, Some of these things are going to have a hard tolerance, meaning a larger tolerance or a tighter tolerance. Like for a hole, typically for a hole, we say to the third decimal place, right? So if this hole is, say this hole is 4 inches in diameter, right? So then I'm going to say 4.000 because I want to have a tighter tolerance for the shaft that's going to go inside of this hole. All right. And so that shaft will probably be 3 point, and I probably have, I don't know, plus or minus 0.005 or 5 thousandths of an inch is my tolerance. So it'll be a 4-inch diameter hole plus or minus 5 thousandths. And then I have my shaft, so because I don't want it to ever be bigger than the hole, so to fit in the hole, right? And so it'll be 3.900 plus 5,000 minus 0. So it could be at the max, it'll be, or 3.89. So at the max, it could be 3.94. And then at the min, it'll be 3.89. So that I know it'll always go inside of the shaft. And then what we call tolerance stack up. We never want a tolerance stack up. And that means where I have my shaft larger than the hole because of the tolerances. If I am ever below 4 inches or 3.95, and then actually my shaft is 3.96, then it won't fit. It's like a tolerance stack up. We don't want that. But in dimensioning, you want to dimension the locations of the holes, obviously, the thickness of this particular object here, the length, and we already went over that. So real simple, easy kind of stuff, right? And so your dimensions will, if you look displaying it, it'll look like so. And you don't want to over dimension it, right? You want to fully define it. You don't want to over define it. That's just bad engineering. It's like, wait, you don't need that dimension there. It's just like having too many views in an orthographic view when you're just giving it to the machinist. Yeah. Any questions? All right, and this just goes into tolerancing and things of that nature. Now, isometric view. What is an isometric view? So an isometric view basically captures all 3 orthographic views in one object. So what does that mean? Well, it means this. I'll give you a view and it'll show you all 3. It'll show me front, shows me the top, and it shows me the right. And it's captured all in one view. Now, typically we don't dimension an isometric view. An isometric view is just giving the machinist or manufacturing facility what the object actually looked like in a 3-dimensional state. Right? So if there's any guessing, hey, let's remove it. Just throw an ISO view on your drawing, and then bam, you got it. It just gives the volume of the object. So if you remember in this definition for your test, it'll be an isometric view captures each of the orthographic views in one view. All right, then you got sectional views. What is a sectional view? A sectional view is used to show, again, things within your object that you can't see. There are sections in your object that you may design that you can't see. What does that mean? Well, let's show this object. This is a perfect object. There are depths within this object that you can't see if you just do an isometric view, right? So you wouldn't know how deep this went if you just did an isometric view. You cut this off and you see how the depths, you see how deep this also goes here, right? And then these depths here, just so you can see all of that, those hidden cutouts that you can't see from an isometric view or an orthographic view. All right. And just another slide that shows sectional views. And then this is an example of a civil engineering drawing. So this is the terrain, and then you have basically the levels of the terrain here. Right now, I'm not really sure what computer-aided tool they use to model this, but for you guys that are going into civil, these are things you may be modeling. Say you're going to be designing a highway and they have you go out and scope the land, and then you scope that land. If you ever see people on side of the highway or side of the road, and they have this little, looks like a telescope on a tripod, and they're looking through it. It's like actually a measure, right? It's like measuring, showing dimensions or levels of the terrain. So I've never actually looked in one of them. I'll just talk to guys that have. So it's pretty cool tool. And it help this little modeling thing that they have, or modeling software Civil's use, helps you to model the terrain. So you'll know basically how you're going to build your highway or what have you, based on the levels of the terrain. So, and then this is a schematic, what we call schematic for a circuit. And the circuit is just showing you where power needs to be connected. It may have some resistors in there, just different components that you're going to be wiring to and from, right? And yeah, and like I said, AutoCAD is used for making these circuits, or PNID, what is like, well, it's not a PNID, but PNID is a pipe and instrumentation diagram, but it's more like instrumentation diagram. AutoCAD is used. And here's another example of an instrumentation diagram. So, any questions on that? And then you have solid modeling, as we talked about. And solid model is just what it says. You draw solid models of an object, and then you can convert that solid model into a 2D model for the machine shop. So it's pretty cool. I think you guys have seen, like, this is actually an example of solid model. Well, where did it go? That's a 2D drawing that we converted from a solid model. This is the solid model, and this is actually a sectional view, right? And so we cut it in half so that you can see the full assembly and what components are inside. All right. All right, cool. Oh, you guys can't see that. I'm not sharing my screen. Wait, let me share my screen. I forget about that. I know you guys are probably like, wait, what is he talking about? Let me share my screen. All right, so this is a solid model, right? And when I cut it, then you see all these other components on the inside that you wouldn't see if I don't show. And so the cut just shows this is a sectional view of the solid model. All right. All right, any questions? Cool. So that's it. That's all I have. Let me look through the slides, see if there's anything more noteworthy. No, don't see anything noteworthy. Oh, one other thing I will add. So you have your different symbols, of course, right? And so these are like, that's the resistor, speaker, capacitor. And then you also, these just two-dimensional symbols. But then there's also this computer-aided engineering software. Computer-aided engineering software is what we use to run analysis on your model, right? So then you want to analyze what loads it'll be able to withstand. You want to analyze which I don't know what kind of civil computer-aided engineering models they would have to sound like that's the simulator that determine how much load a bridge can take, or how well your highway will sustain loads, and what's the lifespan of your bridge. You have these computer-aided engineering softwares that we can run analysis on, like ANSYS for mechanical engineers and Abacus. These are also, softwares we can run, analysis on. But yeah, that's pretty much it. All right. So I'm gonna break you guys up in your groups. I gotta go to my email to figure out what groups are what, and so I can show you guys the platform that we use in class to break you up in your groups, and you guys can stay on, work together, show your faces to one another. You don't have to show them to me. You show them to one another and just talk amongst yourselves to how you're gonna do the group. If y'all already done it, that's fine too. Just still, I'll just introduce you to how we do a breakout session for groups. And so I'll do this whenever you do your presentation for your, no, I won't do it, because unless like there's some in-class work y'all want to do, but we're going to have to stay in one room, which is this room, when we do our presentation. But you'll see what I mean when here in a second. I'm going to stop recording.